Okay, so good afternoon, everybody. Welcome to the first installment of a 4-lecture series. I think the next 3 lectures will be next month, right, Kim?
Yes. This is the first year that we're sort of interdigitating quantum biology with the whole rest of the course. It used to be kind of a separate, component, but now it's weaving in and out of all the others. Yeah.
Maybe you will. Maybe you'll need a break from quantum physics anyway, so this may work to your advantage.
Yeah.
Can you see my slides?
Yes. Yes.
Yeah. Okay, so now we'll go into the presentation mode.
Yeah.
So that's the title, and I believe this is our 10th season, probably 10 years of quantum biology.
Yeah.
Yeah, but that's nothing compared to the 100 years of quantum physics, and it's actually 123 years this year. So,
Cool.
So my name is Jack Tuszynski. I'm a professor of physics, also adjunct in oncology. I spent 15 years in the Department of Oncology, which was the best 15 years of my life. I enjoyed being part of an effort to combat cancer. Now I'm very much into quantum biology and quantum medicine, in fact. So much of what I'll be talking about can be found in these books, which I co-authored. The Emerging Physics of Consciousness, which we'll discuss, I think, in the last lecture, aspects of consciousness and even psychology, concepts from physics which gradually percolate to other fields. I also co-wrote a book on nanoneuroscience, which looks at the nuts and bolts of the various machinery in neurons and in the human brain, and how all of this is supposed to function in concert, and when it doesn't, what happens. And this is now the announcement that Kim was talking about. Coming up this year, Quantum Body. I co-authored a book with Deepak Chopra. Some of you may know Deepak Chopra.
Yeah.
So this book will hit the bookstores around the world. I believe it's going to be published by Random House, the biggest publishing house in the world.
Wow.
And I co-authored the book with Deepak and my colleague Brian Fertig, who is a medical doctor from New Jersey. And Kim, you have a big part in it, although you don't know, because of these lectures which were recorded. And one thing led to another. I collaborated with Brian Fertig on his also 2 books, actually. He published last year on metabolism, and a lot of ideas from physics were used in writing his book. And following on that, we contacted Deepak, and Deepak Chopra and us collaborated for the past year on writing this book, Quantum Body, which has a lot of interesting, visionary, pioneering ideas interspersed with ancient knowledge from Hinduism and other ancient religions. So, yeah, quite interesting. I hope, well, after I published 12 scientific books and 590 scientific papers, I think my reputation is pretty solid in science. So I felt entitled to write something popular. This is popular science. This is not really, there's not a single equation.
Congratulations. Yeah.
Well, thank you very much. I'm kind of proud of it.
You should be.
So now let's dive into the topic. This is the outline for the whole series. I will, because I presume you're not physicists, so I will try to sketch very briefly these ideas that have been percolating from physics to other fields, including and the special biology, but not only. So I'll talk about the world before quantum physics, which means up until the year 1900, and then what happened in 1900 and the following 123 years, namely quantum physics, and then maybe half a century later, quantum chemistry and quantum physiology, and of course quantum biology, which will be the centerpiece of these 4 lectures. But I'll mention also a little bit quantum computing that everybody these days who reads newspapers and watches the news is familiar with. Quantum brain. Actually, this is the title of my next book, popular book. I'm trying to pitch it to the publishing house, a quantum brain or quantum mind, something along these lines. Last year we also completed a very interesting project on probing the depth of quantum biology in terms of the effects of anesthetic molecules on quantum states and in some proteins, which we'll discuss briefly. That will be the next announcement, because you will be the first audience to see the results that we obtained in these experiments that were carried out with my colleagues at Princeton and Stanford, as well as University of Central Florida. Wonderful. And yes, so there's a lot of new things here, and also some old things, because the topic is very old. And then finally, some big questions, whether we can better understand psychology, psychiatry, how the brain works, using quantum ideas, whether it's quantum physics or quantum-like applications of physics, we don't know, but we'll find out. So let me start with this, which is kind of a history lesson in science. At the end of 19th century, there was a very famous presentation to the Royal Society in which Albert Michelson, who was a Nobel Prize in physics, that was before he got the Nobel Prize, he measured the speed of light with Morley and Michelson. He stated in 1894, and this is sometimes incorrectly attributed to Lord Kelvin, but there was Michelson who said, it seems probable that most of the grand underlying principles have been firmly established, the future truths of physical science are to be looked in the 6th decimal place. In other words, this he meant that physics was done and finished in 1894, and what was left is just fine-tuning some numbers, parameters, and basically do engineering. And he was incredibly wrong, because a mere 6 years later, and in the following maybe decade, 2 decades, there was a complete revolution, couple of revolutions in physics. One was the quantum revolution that we'll be talking about, and the second was the relativistic revolution unleashed by Albert Einstein and others. You'll have a close-up look at these people. So it'll be more of a historical overview with some physical concepts, but it'll be physics light. So why is this not advancing? Okay, so before we dive into quantum physics proper, let me just give you an overview of the physics before quantum, the quantum revolution. And basically it was constructed very elegantly, by the way, beautifully, with the 4 building blocks: classical mechanics, going back to Newton, and various reformulations of classical mechanics by Lagrange and Hamilton. And then the second building block was electromagnetism. And I say was, it still is. And we use both classical mechanics and electromagnetism in many applications, but we know that's not the last word in understanding Mother Nature. So electromagnetism, Maxwell's equations, which were the crowning achievement on top of the experimental demonstrations of electricity and magnetism by Ampere, Faraday, and others. And then thermodynamics, which led to the first industrial revolution, as you all know, in 19th century England and other countries. Thermodynamics ushered into the era of locomotive, steam engines, and other applications, and that was constructed by Gibbs, Watt, Carnot, Thomson, Clausius, and others. And finally, where the overlap with classical and quantum ideas can be found is the fourth building block, statistical mechanics, not to be mistaken for statistics. Statistical mechanics is something else, and Boltzmann is the pioneer in this field, together with Gibbs as well, and Nernst and Helmholtz. We'll come back to it a bit later when we compare classical statistical mechanics and quantum statistical mechanics briefly. So in the last 123 years now, we were witnessing a transformation from classical physics to quantum physics, and quantum physics gave birth to quantum chemistry. In fact, chemistry is pretty much all quantum, because chemical bonds involve the sharing, either covalent bonds involve sharing of electrons, and electrons are, of course, quantum particles, or exchange of electrons. Either way, it is a quantum process. And then we have forays into understanding things like metabolism from the quantum perspective, and that's what we call the quantum physiology, or beginning of quantum physiology. And I'll explain to you why it is quantum. And then, of course, quantum biology, quantum computing, and I mentioned these other fields. Now, this is the timeline for the development of the development of quantum physics. We can say that it all started with Max Planck in 1900, precisely. Max Planck introduced the concept of quantization, and that's the origin of the word quantum physics. It's not quantification, quantization, because it means grainness, individual quanta, which can be numbered 1, 2, 3, 4, 5, 6, etc. And that was after many years of trying to explain spectra of black body radiation. Max Planck introduced this revolutionary idea at the time, kind of out of the blue. It was out of necessity, because nothing else works. No classical ideas found in physics before 1900 were able to explain mathematically what was observed experimentally. And then a large number of subsequent applications of quantum reasoning allowed to explain other things. And Albert Einstein was one of the first people to support quantum physics, or quantum mechanics, which is another term for the same field, by explaining the photoelectric effect using quantization of light energy, or photon. So this was 1905 when Einstein got his Nobel Prize. All the people on that list got Nobel Prizes in physics, and they were really geniuses in their own right. And kind of paradoxically, Einstein got the Nobel Prize for what I would consider a less important contribution than the other ones that he made, and special relativity and general relativity, for which he did not get a Nobel Prize. I think he deserved at least 3, but one is, I guess, good enough. And then we had 1913, Niels Bohr in Denmark was able to elucidate the structure of atoms, which then led, of course, to our understanding of molecules and their emission and absorption spectra using quantization of electronic energy. In 1924, Louis de Broglie introduced something which was kind of mind-boggling, and it still is, the idea of wave-particle duality, that in this microscopic world of electrons and elementary particles and atoms, there is no clear-cut distinction between a wave and a particle, because when you think classically, based on our everyday experience, we are used to seeing solid objects. Your cell phone looks solid, your desk or furniture or a ball or a car, everything looks kind of solid, particle-like blocks of chunks of matter. And then when you look at the sea, you see something else. You see waves, water waves, also acoustic waves. Our sound is a wave. And we think that these two things are incompatible, very different. But Louis de Broglie showed that when you look microscopically at these small objects, the smallest objects that make up matter, this distinction makes no sense. And one object which could be seen like a particle, let's say an electron or a proton, in fact, in various experiments, shows its properties which are compatible to those of a wave, and vice versa. Light that doesn't seem to be very solid in terms of mass actually behaves like a particle in some experiments, and I'll show you. So this is that very hard to intuitively grasp concept that Louis de Broglie introduced, and he got a Nobel Prize for it. I think if I remember correctly, he got a Nobel Prize without doing a PhD, or maybe that was his PhD thesis. Anyway, he was a count, and a French aristocrat, didn't need any degrees, but just time to think, and that served him very well. And then we have two other major figures in the world of quantum physics, Heisenberg and Schrödinger. So I'll spend a minute about these two, because they introduce something which is mathematically incredibly elegant, basically replaces this Newtonian world of Newton's equations. You must have heard about Newton's equations, and then extensions to Hamiltonian representations in classical physics. But Schrödinger came up with something which replaces Newton's second law, basically the level of microscopic particles. And Heisenberg did something equivalent to it, but in an even more abstract way using operators. Okay, a lot of this is very technical, so I kind of hesitate to get deeper into it for the fear of losing the audience. But I think at least the names and the general ideas should be covered. Okay, so, and in 1927, Heisenberg formulated what we now call the uncertainty principle. So this is another concept with incredibly important philosophical underpinnings, because until then, most people, including Albert Einstein, and maybe even us, intuitively perceive the world as, to some degree, deterministic, that we can calculate things into the future, predict the weather tomorrow, predict the, well, maybe not the stock market, but anything that is physical. We think we can predict the trajectory of a rocket sent into space. Of course, we do this, but Heisenberg showed that at the level of subatomic particles, at least, we really have no clue. We cannot predict simultaneously the position and the velocity of any object. So you can either know where it is, but we don't know how fast it's moving, or vice versa. We know how fast it's moving, but we don't know where it is. And that applies to other things as well. So this is called the uncertainty principle, which puts everything on its head in terms of our philosophical concepts of we call it determinism. The world, microscopic world, quantum world is non-deterministic. That is, these are the limits to our knowledge. And these days, I think with AI and things like that, we seem to believe in the possibility of almost endless predictability of things. But Heisenberg showed that these are the limits. There is really no way around it. The world cannot be completely knowable. It's not. Okay. And then these other names are very important as well. Dirac, unified quantum mechanics and the special theory of relativity that Einstein formulated. And then we have John von Neumann. You may have known about him. He's also the proponent of computers and computational science. So an early pioneer of several fields, including quantum physics. And finally, in 1940s, Feynman, Schwinger, and Tomonaga fused quantum mechanics with electromagnetism. So if you remember previously, I told you that electromagnetism, Maxwell's equations were one of the building blocks of classical physics. Now quantum mechanics subsumed electromagnetism, and these people got their Nobel Prize for putting this together. Okay, so that's the historical introduction. Here's a picture of these very prominent physicists at the time. I don't want to make any social comments here, but you see that there is a group of old white men and one woman, Marie Curie. So only one woman. Hopefully we'll change that, but that's 1927. It's almost a century ago. And you can see here Marie Curie, Max Planck next to her on her left, and then Jordan, I think, and next to her on her right, and Albert Einstein in the first row. I don't recognize everybody here, but there is Schrödinger in the middle in the third row, and there is Dirac below him. Anyway, all these guys gathered together at these conferences in Brussels at the Hotel Metropole, which I visited. I spent a year in Brussels and couldn't miss seeing the famous hotel where these conferences took place. These were so-called Solvay conferences funded by this chemical company, and they codified the field and created this new fascinating branch of science, quantum mechanics or quantum physics. Actually, initially it was called wave mechanics because everything was represented as waves. Later on, quantum mechanics. Now it's quantum physics. Okay, so I'll now explain some differences between the classical, as we call classical physics, and quantum physics. So in classical physics, as you may have maybe experienced in either college or high school, we deal with point-like objects called particles with masses and their coordinates in space, positions X, Y, Z, and time, and we can follow their trajectories, and we can assign velocities, accelerations. If you ever took first-year physics, I'm sure you remember all of that, and you can probably relax now that you don't have to do it again. But okay, that's particle representation, material objects, their collisions, motion, dynamics, energies, all of that stuff. Now, the other aspect is waves. I mentioned to you that includes water waves, ocean waves, sound waves, radio waves, which are electromagnetic waves, as well as light. And so these are really oscillations in space and time. And waves, by the way, do not move mass. They just represent perturbations in space, which propagate throughout space, but mass is not moving physically. It's just the energy is being moved from point to point. And they can be characterized by their wavelength, so the distance between two peaks, neighboring peaks, the frequency, which is the time distance in time between two peaks, and the velocity of wave propagation, and the amplitude, that is the distance between the top and bottom of the perturbation. Okay, so they also differ in terms of particles and waves differ in terms of their behavior on collisions. So as you know from, let's say, playing ping pong or tennis or balls, any kind of ball, and particles or masses can collide, and after collision they can change their velocity and trajectory. And we talk about elastic and inelastic collisions. In some cases, the two colliding particles can fuse, merge. For example, you could see, let's say, you can throw a piece of chewing gum into a ball, and that'll stick, and the combined object will move a little bit. Or you can, in fact, shatter one object if it's a lot of energy that is given off in the process. But that's not how waves behave. Waves can, both waves can, if you have two waves, they can be superimposed on each other. And when that happens, we can talk about so-called interference, constructive and destructive. The waves can cancel each other, or they can actually create a bigger wave. And they can also pass through each other. So very different from particles, because particles cannot normally pass through each other. They either collide and bounce off or merge, fuse, but not pass through. They are solid after all. Okay, so that's the world of classical physics, and that's not the world of quantum physics. And there was a need for something else, because classical physics could not explain a lot of experiments which were cropping up at that time in the late 19th century. I mentioned already black body radiation, and I'll come back to it again, so you don't have to second guess what it means. And then there were also measurements of atomic emission and absorption line spectra from gases like hydrogen, neon, helium, and so on. Then the structure of the atoms, which was beginning to be understood. I mentioned already the photoelectric effect, couldn't be explained classically. Specific heat of solids, that means how much heat you need to warm up an object by a given number of degrees. At low temperatures, the existing theories couldn't explain that at all. And then we have the Compton scattering over X-rays of electrons or waves colliding with particles, and then what? So kind of a combination of the two, but surprisingly, waves behaved here as particles. So, okay, so quantum theory in essence can be stated as follows, that these microscopic systems not only exist in discrete states, like if you think about a ping pong ball, it's hard to imagine that ping pong ball can be only in a finite number of states or in some discrete states. We think about a continuum, can put them in anywhere in space with any velocity, but quantum objects do not do that. They can be found only in specific discrete enumerated states. It could be an infinite number of such states, but they are clearly distinct. Then the next one is, I don't know if you're very familiar with probability, but I mentioned to you the lack of the Heisenberg uncertainty principle and the end of determinism, and quantum mechanics therefore resulted in the introduction of probabilities instead of specific values of positions or velocities or energies. So probabilities of states. So it's a probabilistic theory. And then, yeah, so quanta I mentioned to you. And there are some quotes about coming from these famous people. Einstein actually never agreed with the basic tenets of quantum mechanics or quantum physics. As he famously said, God does not play dice. Because this is supposed to be the most fundamental insight into the nature of things. So, in other words, what God created, and we try to understand. And if that's the case, then Einstein said, well, I don't like that, because it seems like everything is a probabilistic outcome. So it's like somebody's playing dice with the outcome. And actually now, a century later, we've had experiments. And even this year, not in 2022, the last Nobel Prize in physics was given to 3 physicists who demonstrated that actually God does play dice. That there is actually this probabilistic and well, it's beyond that, it's entanglement, that particles get entangled. Einstein called this the spooky action at a distance. That's another quote from Albert Einstein. That means that quantum particles can be invisibly connected over an arbitrary distance. Even across the galaxies, they still, if you let's say try to find the state of one particle, the other one will automatically adjust to that information. It's really strange, but true. And these 3 physicists, Alan Aspect, Anton Zeilinger from Vienna, and an American Clauser, they demonstrated in 3 independent experiments that this entanglement, this spooky action at a distance, is really happening with their independent work. And so I will mention later on that Einstein was wrong on another occasion. So we think about him as the greatest genius that ever existed, but I think he was a human after all. He made mistakes too. Okay, so, and then we have Richard Feynman, probably the most colorful and the most brilliant American physicist who ever lived. He actually is also considered to be the godfather of nanophysics or nanoscience. Nanotechnology, everything is now nano. So Feynman famously said that there's a lot of room at the bottom. And so he came up with some ideas for how to construct nanotechnology devices about half a century ago, before anybody even thought about this. But he said that things on a small scale behave nothing like things on a large scale. In other words, we have to abandon our intuition to try and understand the microscopic world. But here, of course, we will be talking about biology in March when I come back for this second lecture, and I have to tell you, forewarn you that the quantum concepts, in fact, are not limited to microscopic particles, electrons and protons only, and quarks and things like that. They are also found in macroscopic things. So, although at that time it was thought of as a branch of science really limited to tiny things. And then finally, Niels Bohr, he said, anyone who is not shocked by quantum theory has not fully understood it. And but when I used to teach quantum mechanics to physics, 3rd year, 4th year physics students, I would just say, don't try to understand it, solve the equations and move on. So it's if you spend too much time doing philosophy of science, it's maybe not very healthy. It's better to try and get some some different intuition from the everyday type of intuition by solving problems and understanding the nature of these solutions. Okay, so let's just spend the next 20 minutes or so trying to get maybe deeper into the weeds without too much technical mumbo jumbo, but still, we need to go a little bit deeper to try and understand what quantum mechanics or quantum physics is telling us. So the first statement is true. Classical physics before quantum, so up to 1900, really explains very well macroscopic phenomena, such as billiard balls and rockets. Quantum mechanics, initially at least, was needed and arose as a necessity, not as something fanciful, but a necessity to explain these microscopic phenomena that I mentioned to you. And by the way, a historical parallel is here that I will come back to later on. With biology, it's kind of similar, because in the beginning of the quantum revolution in 1900s, there were just those 6 or 7 unexplained phenomena, very difficult to grasp. In biology, we have a ton of unexplained phenomena, but only about 6 or 7 so far have been analyzed properly with sort of the quantum physics approach. And one of those is photosynthesis, which we'll discuss later on. Another one is bird navigation, which also has recently been explained using quantum phenomena. And there are some other ones, but not many. And we can say, oh yeah, biology, it's very descriptive. We can, blame everything on Darwinian evolution, survival of the fittest, and so on. But if you look deeper, there are a lot of very difficult to explain phenomena, one of which, actually in this book with Deepak Chopra, we delve deeply into it, and that is synchronization. How is it that a well behaved biological organism synchronizes motion and behavior at so many scales of space and time? And I'll discuss the space and time scales in March, and it's a major mystery, and such a mystery can possibly be explained using quantum physics principles. Okay, so, and then here we have a third bullet point, which says that there are, however, very well known, very well described macroscopic quantum effects. In fact, these quantum effects involving superfluids, superconductors, lasers, we all now deal with lasers, laser pointers, scanners, QR codes. It's all based on lasers. This is a quantum phenomenon, and most people who even deal with this on a daily basis don't realize this is all based on quantum physics. As well as kind of trivial things like crystal dynamics of atoms and crystals. We call them phonons, vibrational modes. This is all quantum physics. And magnets. Magnetism is inherently a quantum phenomenon. Without something called spin, which I'll introduce shortly, there is no magnetism. So in a nutshell, what I want to say is that there are several very well-known and very important quantum effects on a macroscopic scale. You can buy a neodymium magnet, very strong magnet at Michael's for $3 or something like this, and this is a very good example of a quantum system. Okay, now, all of this requires very important what we call formalism. That means a mathematical representation of physical properties. And this, another historical tidbit, this was very conveniently developed prior to the onset of quantum physics by mathematicians. In the 19th century, mathematics developed something called functional analysis, which involved the mathematics of so-called Hermitian operators and introduction of Hilbert spaces. Again, technical terms, but if you ever take quantum mechanics, these are the tools with which you build the physical representation of this macroscopic world. So suffice it to say that mathematics, without any projected utility for these things, created all the entire toolbox for physics almost a century before. And that's another important lesson, I think, in our technology obsessed world, that sometimes you make discoveries which seem to be completely useless, but then after a period of time it turns out that they are incredibly important in the future. And that was one such set of discoveries, mathematical fields that physics utilized to build first the understanding of the microscopic world, and later on, much later, all of it turned out to be of cardinal importance in technology. So I mentioned lasers and computer hardware. All of this works on the semiconductor technology, which is based on quantum physics. Okay, so now let's talk about some more specific basis for quantum physics. So I told you about the importance of the wave-particle duality, that we have to abandon this this vision of the world as composed of solid objects. Think more about cloud-like structures, which can spread in space and time and propagate through time. These are better representations of the units of matter. And then instead of certainty, we have to talk about probabilities of things happening or evolving. Probability, just like you can have a weather forecast with 7% probability of snow tomorrow. So that's all we can do in the quantum world. Maybe you can go to higher, 90% of something, but there's always the lingering uncertainty that this may not happen. And then there is something really philosophically intriguing, and I want you to think about it, because I think most of the time, well, let's say we make an observation as a scientist, you want to be very precise, very accurate. And you, even as a biologist, let's say you want to observe animals in the wild without disturbing them, right? So be very objective, no interference. And we think that we can do this, or the same in, let's say, psychological tests. You don't want to affect the person you're interviewing. Well, that's fine, but in the quantum world, it's not possible. There is no possibility of any measurement at the microscopic level or quantum level without interfering in the system. So that's called the observer problem. The observer changes the observed always, because you have to use, even the tiniest tool is comparable to the object. So let's say if you use a single quantum of light, a single photon, to observe an electron, it'll really hit it like a hockey stick hits a puck. You cannot interrogate the system without changing it. So that's a very fundamental thing. And some people say, for this reason, there is no objective reality. That is, something doesn't exist until you measure it, and when you measure it, you change it. It means that then the reality becomes subjective. So it depends on the way you interfere with this object that you want to measure. It's kind of difficult to comprehend how the world can be understood without changing it at this level. Anyway, so something to think about if you have nothing better to think about. All right, and then And then this quantization, the term quantization I mentioned to you comes from the fact that energy cannot be subdivided into fractions of units. It really exists only in integer numbers of units, 1, 2, 3, 4, 5, and so on, not 1.35 or 2.4 or something like that. Okay. So there are a lot of philosophical differences, and people are studying this even today and arguing and debating fine points of the implications, because the classical world was more or less completely knowable, and famously Simon de Laplace, one of the contributors to classical mechanics, stated that knowing the position and velocity of physical objects would allow him or us to completely predict the future of the entire universe. If we had all the positions and velocities, then we could. So it's kind of like a clockwork representation of the world. But that's not the case with quantum particles. Even one, you can't even predict the future of a single electron. You can only, as I said, predict the probabilities. But that's not the same that this must happen. This may happen. Okay, so this is called the Copenhagen interpretation of quantum mechanics, which is probabilistic. And I will, in a minute or two, explain to you how these probabilities are related to other properties. And okay, that I mentioned to you Heisenberg uncertainty principle, the observer problem. And in spite of all of this, it's kind of paradoxical that we still understand the world better in spite of all these caveats that, oh yeah, you can't do this, you can't do that, but we still get a better glimpse into the nature of things. Okay, that's the wave nature of matter and the particle-like nature of waves. So both particles behave like waves and waves behave like particles. And this is one of the applications of so electrons, which we think of as tiny little balls, the size of about a picometer, 10 to the minus 12 meters, can be scattered and diffracted on diffraction gratings, and you can see here representation of such scattering, which looks almost identical to the diffraction patterns of light. So they behave like waves passing through slits, and a single electron, if you have two slits through which an electron could in principle pass through, it will pass through both at the same time. So imagine that you have a ping pong ball and there are two openings in front of you, and you try to throw this ping pong ball, and it will go through both openings at the same time. It's almost like has a double of itself, right? So that's what happens at the level of electrons and protons. And importantly here, I think I have an explanation. No, maybe later. So there is lambda is a wavelength. So we talked about what the wavelength is. Let's say the wavelength of an ocean wave could be a few meters, right? But here you can calculate the wavelength of an electron, and it's comparable to its size, so it's very small. But you can see de Broglie, for his Nobel Prize, he derived this relationship, the de Broglie relationship, which is the wavelength of any object, and that's inversely proportional to its mass. So the bigger the mass, the smaller the wavelength. So when you go into macroscopic objects, the wavelength becomes tiny. In other words, the quantum aspect of it gradually disappears as the sizes increase. I think I have another slide which shows visualize this a bit more directly. Okay, so Max Planck, I mentioned two blackbody radiation, and this is the famous formula, which is in red. So this is what he kind of pulled out of a hat in order to explain this. The graph at the bottom on the right-hand side is the observed spectra of emitted light or electromagnetic waves in general from objects at different temperatures. You see 2000 K, 2000 Kelvin degrees, very hot, 1750 Kelvin, less hot, but still very hot, 1500 and so on. And you can see the peak of this spectrum moves to the right as the temperature decreases, sorry. And that's called as Wien's displacement law. And that's in the middle, lambda max times temperature equals 2.898 times 10 minus third meters Kelvin. So that formula was so difficult to explain until Max Planck came on the stage. Now, and he came up, and I have no time, or you have no need probably to understand the nuts and bolts where it came from, but the formula that is in blue at the top is Max Planck's fit to these curves, and that little thing in the denominator, e to the power hf divided by kt, is the key to the quantum world. And that means, okay, let me rephrase it. It was really guessed by Planck. He said that energy of electromagnetic waves is proportional to their frequency, and the proportionality constant h is the Planck constant. It's one of the so-called fundamental constants of the universe. We don't know where it comes from. There's no explanation, and there are several of these. One of which is the speed of light, for example. It's 3 times 10 to the 8th meters per second. The Planck constant is here, 6.6261 times 10 to the minus 34th joule seconds. So it was an empirical fit to a formula which explains observations made in something like 1860 or something like that. It turned out to be one of the most important pieces of information about our universe. I mean, this is mind-boggling, right? Curve fitting gave us the opening to a new world, to a new understanding of our world. And it turned out that this constant is a fundamental property of the universe. And it can be found also in other manifestations, including this Heisenberg uncertainty principle, which I'll talk about in a few minutes. And yeah, and Planck kind of winged it. He came up with this formula in the red, and energy equals n plus 1/2 hf. This is the same hf, Planck constant times the frequency. So two important things here. Number one, connection between the frequency of waves and their energy that was, again, purely empirical at that point. The second is this quantization that means n equals 1, 2, 3, 4, 5, etc. that nobody knew about. That's the quantization par excellence. 1918 Nobel Prize for something as simple as this formula. And then lastly, the constant h, which is, we still don't know where it comes from, but it rules the universe, basically. Okay, so this is kind of a pedestrian overview of the importance of this Planck's radiation law, explanation of things that people were trying to explain for decades, and he came up with this. Okay, and then, so remember h, the Planck constant, right? Then Einstein in 1905 explain this photoelectric effect I mentioned. So what is this? And again, experiment was done with incoming light, 2 electrodes, 1 emitter plate, 1 collector plate. The light triggered, shining on the emitter plate triggered the flow of a current, provided the color of the light was blue. When it was red, it wouldn't do it. It turns out that blue has higher energy, higher frequency than red. Red has a lower frequency, and that was paradoxical. Why? And no matter how much of that light would be shining on the emitter plate, if it was red, nothing would go. With blue, intensity of light didn't matter. It was leading to the current flow, which was measured by an ammeter. The circuit was closed. Okay, so what does it mean? Well, this is what happens. This shows that light, or quanta of light called photons, behave in this case like particles. What they do is they basically hit the metal, the emitter plate, and as they do so, if they have enough energy, they will eject an electron, kick it out like a collision, So, and if that happens, this electron then, being freed from the metal surface, would then be attracted by the opposite charge on the collector plate, the positive charge. Electrons are negatively charged and will travel there. So Einstein came up with this, and and guess what? Everything checked out, provided the energy of this electron, of this photon that kicks out the electron, is proportional to the frequency, like Planck postulated, just guessed, and the proportionality constant is the same h, Planck constant. So a completely different experiment and the same representation of the energy of light. That was amazing. That was the second proof that something completely different is going on. So light is quantized in the form of photons. By the way, Sir Isaac Newton, 300 years earlier, 350 in fact, I think, envisaged that light is actually made of balls or particles. So of course he didn't know anything about quantum mechanics, but so that's the wave particle duality here, and showing you that the photoelectric effect is cannot be explained in terms of waves alone. It has to be particle representation of light, and there are some so far let's just stay with this. This is the third event that showed the same constant that Planck postulated in a completely different context. Heisenberg uncertainty principle I mentioned to you. This is in a mathematical form. It says the following: delta H is the position uncertainty. Should be uncertainty, not uncertainty, sorry. Which means the error that you, let's say, inevitably, the smallest possible error that you can inevitably find in an experiment. In position, error in momentum, uncertainty in momentum, delta P. Momentum is mass times velocity, so it's like proportional to velocity. And Werner Heisenberg came up with this formula, which says that the best you can do in terms of uncertainty, a combined uncertainty of position and momentum or velocities, guess what? The Planck constant, h, again, divided by 4 pi. So same number, third time, no accident, cannot be an accident. It turned out to be fundamental. So by the way, the same applies. So it tells you that, as I mentioned, you cannot simultaneously be certain of where something is and how fast it's moving. That's right. You can know one of these two things perfectly, but the other you lose knowledge completely. Or you have some knowledge of one and the other, but imperfect, and there is no way around it. You always are limited by these by these two uncertainties. And by the way, it also applies to several other properties, not just position and velocity, but also energy and time. For example, if you want to know precisely the energy of something, you will not know when this energy was not measured, but attributed to this object. So if you know perfectly the energy, you don't know exactly when it was, or vice versa. If you measure at this precise moment in time, you will not know what the energy was at all, or partially both. And also applies to other things like angular momentum and angle and so on, but we don't need to go again into too deep into it. And I think I'll finish today's lecture with something which you probably know quite a bit about, namely the structure of the atom, the sort of planetary representation of the model of the atom. It started with Ernest Rutherford, who in his lab determined that the atoms are constructed from the positively charged nuclei, which later on we learned contain protons and neutrons. Protons are positively charged, neutrons neutral in electrostatic values, and electrons. And I think there was initially a model of like a jelly, that electrons were forming a smeared out mess, but it turned out that it's more like a planetary model. That was Niels Bohr's contribution to quantum mechanics. And here it is. Instead of a jelly, electrons form very well organized orbits. I will say that that's still an approximate representation. We don't want to go too deep into it. But what's important is that these electrons occupy well-defined states, and they don't fall on the nucleus. If you remember electrostatics, opposite charges attract, right? So you'd expect negative electrons to be attracted to the positive protons in the nucleus and collapse on the nucleus. They don't. And Niels Bohr explained it using this new field, quantum mechanics, and demonstrated that they occupy stable orbits. So without quantum mechanics, we wouldn't have stable matter, because everything would collapse. Atoms would be all concentrated in the nucleus, and there would be no possibility of having different types of atoms. Everything would be just a point-like aggregate. Okay, and this is more or less what we mean by this. You have these orbits, x equals 1, x equals 2, 3, 4, and each. Now, now this is, you see the Planck constant for the fourth time. How do we relate the Planck constants to these orbits? Well, it turns out that these electrons, each orbit has a different energy, but you can change the location by either giving them energy by photons. So they absorb the energy of a photon, they can jump to another energy level, another orbit, a bit like going up the steps. You need to put a leg up, and that takes energy to go from the bottom to the top, right? Or if you go down, you emit energy. Well, we don't emit energy, but the electrons do. And these are emission spectra. When the electrons come down to a lower energy level, they emit light, electromagnetic waves, photons. Or if they go up on that scale, they absorb. So these are emission and absorption spectra, and different series. And what's important here is that the difference between these energy levels is always given by, guess what? H times F, the Planck constant times the frequency of light. So by measuring this frequency or looking at the color of light, you can deduce which energy levels the electrons changed, because the difference in the energy is proportional to the frequency. And this is the basis of atomic and molecular spectroscopy, based on this, we can figure out the composition of stars in different galaxies because we analyze light coming from stars. Based on this, we can determine the pollutants in the atmosphere and pigments in the paint, emission composition of stars, monitor car exhausts. We can also analyze metabolites. It's the entire field of spectroscopy is based on this. So a simple, very simple formula. Again, Planck's empirical assumption led to so many different advances in our understanding of science and nature in general. So different energy levels also involve what we call rotational degrees of freedom or vibrational degrees of molecules. They vibrate or rotate, and you can change these degrees, these energy levels, by absorbing or emitting electromagnetic waves, and all of it is quantized. So let's see. I'm almost done. I didn't cover. Oh yeah, this is the slide that shows you the wavelength from the Broglie formula, and again you have Planck constant for the 5th time. So obviously it's not an accident, not a coincidence, but something very, very important because it shows up again and again and again. So just very quick comment. If you would ask me why isn't your ball pen cap a quantum object or manifestly quantum object, everything is in some deeper sense quantum, but you can't see the wave function of this macroscopic object, is because the wavelength lambda in this case is calculated to be 10 to the minus 31st meters, but its size is 3 centimeters, 0.03. So it's just the wavelength, the quantum aspect of it is so tiny, 29 degrees, 29 orders of magnitude smaller than the object. You can't measure it, let alone see it. On the other hand, the electron with this energy 1 eV has the wavelength of 1 nanometer, 10 to the minus 9 meters, whereas the diameter of an electron, in stationary electron, is 2 picometers. So the quantum extent of an electron, think about it as a cloud, in this case, not a ball. If you think about it as a ball, it's 2 picometers, 2 times 10 to the minus 12. But in essence, with this energy, it's spread out over 1 nanometer. So it's almost 500 times bigger as a quantum wave function than if you think about it as a ball. Okay, so this is just a list of other experiments that showed quantum nature of the microscopic universe. Why is this again? I don't know. I said that already. So I will finish with, so I have about 5 minutes, less than 5 minutes, I think, with the very quick rundown of the postulates, because I remember the Solvay conference in Brussels. These 30 or so Nobel Prize winners got together and they came up with this list of postulates framing the field. It's almost like the framers of the Constitution of the United States, the founding fathers. They were the founding fathers of quantum mechanics. They got together and say, okay, this is our Constitution. And so they came up with 4 postulates of quantum mechanics. And the first postulate is that microscopic objects are represented by abstract functions, mathematical functions, which we call them wave functions or eigenfunctions. Let's say wave function represented by this letter psi, Greek letter psi in this case. And that's the first postulate. Forget about position and velocity that you were taught in either high school or first year physics. Now you assign a wave function psi. Okay, take it or leave it. That's Schrödinger. By the way, we'll come back to this guy because he wrote in 1943 or 4 during the Second World War he was exiled to Dublin in Ireland. He wrote a very influential book called What is Life? Can you believe this? Yeah, I strongly recommend you read it. It's a very small, short book, very interesting. So he came up with this wave function psi of psi and t, and it's a complex number. When it's multiplied by its complex conjugate, it gives you the probability function. So the square, in other words, the square of this function gives you the probability of something being somewhere at some time. Okay. And these are the properties. Let me just say only one thing about the wave function. Because the square of it has to be a probability, then when you integrate, add up all the probabilities over all space, that has to add up to 1. We call it normalization. So there are some properties. I don't want to say too much, but the bottom line is this, that's how you calculate probabilities and link it to real observations, because you need to have something to connect mathematics with physics. And okay, so the second postulate of quantum mechanics is here, linking the wave function to a probability. And by the way, one more thing. Yes, the wave function says it's a state, and if you have two states, you can add them up or subtract them, and you still obtain another state. So one of the weirdest things in quantum mechanics is that any microscopic object can be in any number of states at the same time. We call it the superposition principle. I don't know if you heard about the famous Schrödinger cat paradox. No? So it's a mental experiment saying that, well, if that's true, that any quantum object can be in a superposition of two states. So a cat can be, if you don't see it, you put it in the box, and that experiment is a bit longer, and I don't want to spend too much time on it. But in principle, a cat can be dead and alive at the same time in a superposition. So you can kind of make fun of this superposition principle, but in the microscopic world, without a doubt, these microscopic systems can be in any number of states at the same time. It's a bit like we are, I guess. In reality, you may be in Edmonton. I'm in Italy, by the way, but in fact, we're kind of like in both places at the same time. I'm to you in Edmonton, and you are to me in Italy, because here I am. So we are in a superposition state. Okay, so that's that. And this is the hardest. I don't want to go too much into mathematics, but things that you know and I guess cherish from everyday experience, like mass and position and velocity and things that you can actually touch and measure, become mathematical differential operators. So it's a derivative with respect to position is related to velocity, and energy is this formula. Well, we have no choice, but we have to take it because it works. But that's the third postulate of quantum mechanics, that these are so-called observables: position, momentum, energy, angular momentum, become mathematical operators. And the fourth postulate, the last one, is Newton's equations of motion are replaced by the Schrödinger equation, which is written here. It's a second-order partial differential equation, which basically tells you how to calculate the evolution or the future of the state of any system based on the interactions it's under. So if you know what it interacts with, and the evolution is on the right-hand side, is the time derivative dt of psi of the state, and on the left you have the energy, is driven by the energy. The second derivative with respect to x, dx squared with the, again, Planck constant, h squared divided by 2m, is the kinetic energy. That's the, kinetic energy mv squared divided by 2, remember from high school? Now it's a second order partial, okay, partial derivative with respect to position. And v of x is potential. So it can be a particle in a well or in the presence of a spherical potential or something like this. So this was postulated by Erwin Schrödinger, the same of What is Life, in the 1925 work. And by the way, there's an anecdote. I'll just finish with this anecdote. Schrödinger spent 2 weeks skiing in, I think, February 25 in Switzerland. And he spent 2 weeks and came up, after skiing, he came up with this equation and he got Nobel Prize for it. So I guess what it says is that you should go skiing to Banff and maybe think about some big ideas, and who knows, maybe that'll lead to a Nobel Prize, because that's kind of good practice. All right, so that there you go. This is it. The Schrödinger equation, without too many details, looks like this. It basically gives you the energies of the system, E, and also the time evolution. So the probability of the system going to different states. Okay, that was probably the hardest part of the course. A lot of new ideas, new concepts, but things get better from now on.
Yeah.
So I thank you for your attention.
So the students are responsible only for the really big ideas here, and the test in this area now is multiple choice. So yeah, I just don't want you to be scared about having to memorize formulas or calculate stuff. If you were in physics, you would have to do that, but you're not in physics. So
count your blessings.
Yeah, you don't have to.
But big ideas, yeah, right. Big ideas. There's a lot of big ideas, and I think so. As this progresses, we'll talk about how these big ideas can help us understand living systems, and especially eventually the human brain. You know, because I think you may already see a lot of things that our mind or our brain could be understood better if it employed quantum mechanics. Maybe not
okay
yet, but...
So I just wanted to say one other thing about Thursday. You remember the last time we had a Shauna Pandya workshop, we had some people there who weren't actually registered in the course. This time it's different because we're using virtual reality headsets, but I think it's still game if you want to. The same friends and family members and so on that you reached out to for that other workshop. If you wish, you could ask them to come again. We'll be sharing the headsets, but yeah, I just wanted to say that is possible. And I think this teaching session today is a very good stimulus. You know, as you go through the time between the second, third, and fourth lecture in March, you know, think of how the concepts of quantum biology really apply to everything. So, you know, you can think of them as being a part of every other lecture in the course, but sort of unspoken. And it's one of the unique features of this course. The other things we teach in this course, you could learn in some other course, but you won't find such a coherent presentation of quantum biology anywhere else, I think. So it's something to really treasure and think about. And don't worry about not understanding everything. I don't think anyone understands everything in this area.
Well, you remember the famous words of the Nobel Prize winners, you know. So nobody really understands it. I think we have to get used to some some of these paradoxical ideas. But such was, and I went to India once. I was invited to one of the Indian Institutes of Technology, and they were trying to introduce quantum biology as a program. And you know, they invited people from all over, and I told them, you know, this is too difficult, and they said, don't worry, we have 1 million applicants, and we select about 100.
Wow. It's the elite of the elite. Yeah, well, that's fun to think about. Yeah, I think anything that you're deeply into and you think you understand it all, you should go to India and then teach the same thing. And you'll realize there's still stuff you don't understand. Yeah. So yeah, it's a way to stay humble. And you know, and where you expect to find dust. I visited one of the richest people in India, and there are parts of that house that had never been dusted. It was like the most amazing thing. Who would imagine? Yeah. So, okay. Well, we
See you next
look
month.
forward to your 3 lectures in March. We're very excited about your books and future books. And yeah, it's nice to have contact with you, even from Italy to Edmonton. That's kind of fun too. And thanks for staying up late to talk with us. Yeah. Okay. So thank you, everyone. And for the students, we look forward to face-to-face virtual reality on Thursday. Okay. Take care. Bye-bye.
Bye-bye.